Hello, dear viewers. Welcome, everyone. I am Jet Aguilar from the Astronomical League of the Philippines, and I will be your host for today's webinar. Thank you so much for joining us to our seventh webinar of the Astronomical League of the Philippines Astronomy Expert Speaker Series of 2022. And I am happy to see that a lot of registrants attending are not only from the Philippines, but from all over the other countries around the world. And we are very fortunate to have with us today a very familiar name among amateur astronomers all over the world, none other than the editor-in-chief of the prestigious Astronomy magazine. He will be giving his talk entitled Galaxies Inside the Universe's Star Cities. My fellow ALP member, Ms. Imelda Johnson, will be introducing our speaker later. For those who were not able to register, but who would still want to watch this webinar, we are currently live streaming on Facebook Live at the Facebook page of the Philippine Astronomy Forum, as shown here. And before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. So enjoy the webinar and have fun learning. And this will be the program flow for today's webinar. Let me turn you over now to our president, Mr. James Kevin T, to give his welcome remarks.
Thank you, Dr. Jet Aguilar, for the nice introduction. Good morning to our viewers in the Philippines, and good evening to our guests in the United States and Europe. My name is James Kevin T. I'm the current president of the Astronomical League of the Philippines. On behalf of ALP, I would like to welcome you all to our Astronomy Expert Speaker Series of 2022. This webinar is part of ALP's International Astronomy Education Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people and to the rest of the world. Thus, that is why the webinar is being offered free to the public. I would like also to take this opportunity to thank ALP members who have been instrumental in putting this program all together, especially Imelda Johnson, Edith Aguirre, Dr. Jet Aguilar, Jun Lau, Henry Colty, Andrew Ian Chan, and Peter Benedict Tubalinaw. So this is the seventh in our speaker series. The first one, which was given by Professor Jay Pasakoff of William College, and this was followed by Mr. Zolt Levey of the Space Telescope Science Institute, then Mr. Joe Rayo, which was followed by the Mr. Eclipse himself, Fred Espenac, then Robert Reeves, and Ken Crawford. So for tonight, our speaker will be the famous Mr. David Eicher, editor-in-chief of Astronomy magazine. We have more distinguished speakers lined up for the upcoming months, so please stay tuned and please do not forget to register in advance for this future webinar. Thank you very much. And now I would like to turn over the program to Imelda Johnson, who will introduce our guest speaker for tonight.
Thanks, James, and thanks everybody who's attending. I'd like to welcome our guest speaker, a good friend, Dave Eicher. Like many of us attending this webinar, our speaker today started out his career in astronomy at a very young age of 14. And at 15, he started his own amateur publication, Deep Sky, even before he joined the parent company of Astronomy magazine. His love and passion for communicating the science led him to the reins of one of the world's leading magazine on the subject, Astronomy magazine. God, Dave, I can't believe I was able to say that. I hope nobody from S&T is listening. Dave Eicher has been with Astronomy, that is the magazine, for 36 long years, of which for the past 20 years he has served as editor-in-chief. Dave is a prolific writer who has now written 26 books, 2 of which he co-authored with an astrophysicist rock star, Ryan May, from the famous band Queen, as in Bohemian Rhapsody Queen. For Dave's many contributions to the science, he was honored by the International Astronomical Union in 1990 with his own space rock by naming asteroid 3617 Eicher. Edwin and I have known Dave since the 1990s when we first met him at a star party. You see, Dave is a highly sought-after speaker at astronomical meetings, conventions, and by the various news media. Although we came from 2 different and competing teams, we were able to remain friends and work together in producing 2 world-class magazines in astronomy, Sky and Telescope and Astronomy. But before I turn over the screen to Dave, Edwin and I would like to share a historic photo during one of Dave's visits. Here is a rare photo of the 2 editors-in-chief, Dave Eicher of Astronomy and Peter Tyson.
To share my screen. Sorry.
Sorry, are you able to see that?
No. Share screen. Yep. Share screen.
So are you able to see it now, guys?
There.
Okay. Share. Yeah. So that's Dave Eicher. Are you able to see it, guys? Yeah. Of Astronomy and Peter Tyson of Sky and Telescope during our 2016 wedding anniversary dinner here at home. I've seen both editors attend conventions together, but I think this may be the first private home party I've seen both of them together. Correct me if I'm wrong, Dave. And
I think you're right. Yeah.
friends, let us welcome Dave Eicher.
Well, thank you very much, Imelda, and thank you for having me. It's a pleasure to be with all of you, and especially to see some old friends among the group, Imelda and Ed and June and James and others. Some of you I've known for a long, long time, and so thanks so much for having me. Imelda, you wanted me to talk about just for a minute about how I got into this before we start. So I was the son of a professor of organic chemistry at a university in Ohio called Miami University. And so I grew up around a chem lab and very involved with science from a very young age, going over to the university there after school and all kinds of things. Well, you never want to do, at least exactly what your dad did. So I was interested in science, and I sort of thought I wanted to be a physician when I was very young. But then I made the decision to go to a star party, and in one of those old Criterion RV6 dynoscopes, caught my first glimpse of Saturn, and I was immediately transfixed and just blown away that you could go out from a house in a neighborhood suburb in a small town with a reasonably dark sky in those days and aim this thing up and see the golden orange globe of Saturn and its rings. It was mesmerizing to me. And so I was just awestruck and immediately got interested in that. And it turns out that the local club newsletter was had someone who was writing a column about so-called deep sky objects, star clusters, nebulae, and galaxies, who had just retired. So who better than to get to take over writing this column in a little newsletter than the young kid who doesn't know what he's doing. So they enlisted me to do that, and that led to this little publication, Deep Sky, which caught on, and that led me to astronomy. And I had the good fortune to be in touch with lots of people early on with the magazine and with other efforts. And Carl Sagan was very, very nice to me and encouraging with all sorts of advice. But in the end, I had more fun writing about this stuff, I anticipated, than I would have had as a professional astronomer. So I bailed out and became a journalist and got to be friends with both the folks at Sky. You know, I was good pals with Dennis DeCicco and Norm Sperling at the time, and Kelly Beatty and others, and also Richard Berry and Robert Burnham at Astronomy. And so I knew I wanted to go to one of those two places, and the rest, they say, it's been a lot of fun. It's actually in this September now will be 40 years that I've been at Astronomy. So it has been a lot of fun, and I'm getting late in the game here, but there's tremendous stuff. You know, as we know, we're in a golden age of astronomy. There's more research going on now than ever before, by far. It's a very exciting time. And next year, Astronomy magazine will celebrate its 50th anniversary with all sorts of special events. So it's been great fun. And one of the things that I really loved when I was very young was a book called Galaxies that Tim Ferriss wrote, a great science writer and a kind of a hero of mine early on. And I thought, you know, one day I'd love to write a book about galaxies. And that book came out in 1980, Tim's book. And it turns out that essentially the whole field of galaxies, what we know about galaxies, has changed in that generation since 1980. So I published a book a couple of years ago that came out just on the cusp of the pandemic, called Galaxies. This came out from Random House and is sort of an update, if you will, of what we know to the present. So I'll be sharing a little bit of that information today. So I will go ahead and share my screen. And I lost it here. Let me share the screen here. And can you see that okay? Can you hear me okay?
Yes.
Excellent. Well, I will take it away and start. And again, it's been a great pleasure to know some of you, and I'm quite honored to be here with you today. Well, this whole story of galaxies really began to transform in a modern way on October 4th, 1923, when a young and fairly brash astronomer, Edwin Hubble, who wasn't everyone's favorite. He was not the easiest guy to get along with, but he was very, very interested in what at the time were called spiral nebulae. And the nature of these objects was mysterious and unknown in the 1920s, even after this great debate between Shapley and Curtis about the size of the universe and the distance scale and all that kind of thing. And so Edwin Hubble, this very young professional astronomer who was trained at Oxford and was from Missouri originally, he spent a lot of time in and around Los Angeles and had the good fortune of using the largest telescope in the world at the time periodically, the 100-inch Hooker telescope, which oddly enough, you know, the largest telescope in the world before that, going back into the mid-19th century, was Lord Rosse's telescope in rural Ireland, which was an amateur telescope. Well, by the time of World War I, the Hooker telescope was the first really large professional telescope in the world. Los Angeles at that time was a very primitive and different place than we're kind of used to now. It had a population of about 1 million. At Caltech, Robert Millikan had just won the Nobel Prize in physics for measuring the charge carried by a single electron and for the photoelectric effect. Across town, a young flyer, Amelia Earhart, was taking flying lessons, and a young cartoonist, Walt Disney, showed up in the town of Los Angeles with $40 in his pocket, hoping to make a living, and it worked out pretty well for him. So on Mount Wilson, every few nights that he could, Hubble drove up from Pasadena and was imaging spiral nebulae, very interested in their nature. And one of his favorite objects was the Andromeda Nebula, as it was called then. Most people at the time, most astronomers, believed that these spiral nebulae, and a notion dating back to the 17th century, were objects that were in our galaxy, in our local universe. However, Hubble took a very famous couple of plates late in 1923, and he took this second plate, which I'm showing now, which became one of the most famous photographs in the history of science, because he thought he, with quite a sense of amazement, had discovered a nova in this object. And you can see it near the top, the tick marks and an N, which he subsequently crossed out, N for nova. Well, he took this plate back down that was taken on October 6th and studied it subsequently in his office in Pasadena, and suddenly discovered from previous observations, both at Mount Wilson and elsewhere, that it was not a nova. It was a variable star, and you can see he crossed out the N and wrote, very famously wrote, "ver!" exclamation point. Much to his astonishment, he discovered that it had a regular and very recognizable pattern of brightening and dimming, and that it was a so-called Cepheid variable named after Delta Cephei, the prototype in Cepheus. And it was incredibly dim. And of course, the absolute brightness of this kind of variable star is very well known, was very well known at the time as well of World War I or just the early 1920s. So he was stunned because this was much, much, much fainter than any other Cepheid variable star known. And because the absolute brightness was known so well of this kind of star, he could calculate the distance to this object. He was just about fell out of his chair because he calculated the distance to the Andromeda Nebula as 1 million light years, which was 3 times the size of what most astronomers believed was the entire universe at the time in 1923. Now we know that he was off a little bit, and that's 2.5 million light years away rather than 1 million. But this was a breakthrough observation, and Hubble, to his incredulous, stunned nature, both discovered the first hint to the enormous, what we now call, of course, the so-called cosmic distance scale, but he also discovered the nature of galaxies as large systems of stars, gas, and dust that are very far away. So this was an incredible moment. Looking back at other research that had been done even previously, he found that others, like, and I will make a little bit of a statement here for an institution that I love and I'm also allied with, Lowell Observatory, and that is that in 1912, even before Hubble's breakthrough observation, an important astronomer at Lowell, V.M. Slipher, very carefully had a Massachusetts-made spectrograph that he began using and discovered that many of these spiral nebulae had very high velocities and appeared to be moving away from each other. And so that was the first clue at the so-called universal expansion of the universe, that on the whole, galaxies are all moving away from each other. So this was really sort of a huge moment in astrophysics, which had only begun about the time of the American Civil War in the 1860s. And we realized for the first time that there was an enormous universe of galaxies out there, and that the universe was expanding. And if you rewound the history of the universe backwards, you would reach a point of origin that we later came to call the Big Bang. So this was a big, big time in the history of astrophysics. Well, as with all sciences, however, we didn't have the kind of sophistication then that we have now. Early days of galaxy research were largely an effort of classification, whether it be mineral specimens or bones or postage stamps or old letters, whatever it is, to understand things in the universe. Scientists have to classify them first. And so for a long, long time, Hubble and others worked on galaxy classification. In the 1930s, and he published his first results in a very famous book called The Realm of the Nebulae that was published in 1936. Hubble worked for a long, long time on classifying galaxies, and he worked out the famous, what we call the tuning fork diagram of galaxy classification, working on three basic shapes: spiral galaxies like this one, this is NGC 2841, barred spiral galaxies, and elliptical galaxies, big, disorganized, essentially spheres. But it was interesting that most galaxies that were observed at the time seemed to have some kind of an organized disk. Well, the classification went on for a long, long time, and essentially used and expanded Hubble's system from the 1930s into the late 1950s, until another fellow who was a brilliant guy came along after Hubble's time, who was a French-born astrophysicist who made his way eventually over to the University of Texas. And I had the great fortune, maybe some of you met him as well, but to know him in the later parts of his life, and his name was Gerard de Vaucouleurs. And de Vaucouleurs came up with a much more sophisticated set of criteria for organizing and classifying galaxies called the de Vaucouleurs scheme. And it is sometimes called in a sort of a three-dimensional diagram that uses slices along this football-shaped sort of classification that incorporates all sorts of other kinds of phenomena that Hubble really didn't get deeply into. Details on the bars of galaxies and how they are shaped and formed, whether a galaxy shows rings of encircling matter, how tightly or loosely wound the spiral arms are of a galaxy, or so on. And we still use the de Vaucouleurs system today. It's sometimes nicknamed the cosmic lemon because it's more or less lemon or football shaped like that. So that's the system that we still use that really was introduced in the late 1950s. By the mid-20th century, astronomers realized that galaxies are the basic building blocks on a relatively large scale of the universe. Their stars, their gas, their dust contains most of the visible matter in the cosmos. And for years, astronomers estimated the number of galaxies at about 100 billion galaxies in the universe. And we'll get to some fine points about that later that complicate the issue. But for the moment, let's think of roughly 100 billion galaxies in the universe, and how they got to that number was, you know, many of you know there's this series with the Hubble Space Telescope of so-called deep fields and ultra deep fields. And the best ultra deep field, which is a tiny piece of sky in the southern hemisphere, which shows 10,000 galaxies in a tiny field of sky and a couple of foreground stars in our galaxy. Extrapolating that number over the whole sky is essentially how we get to 100 billion galaxies. However, as you guys know very well, I think, because I've known some of you for a long time, telescopes are time machines. And when we look at distant things in the universe, we're looking far back in time. So when we talk about galaxies and 100 billion of them, we're talking essentially at the present day universe. Galaxies, it's become clear since the 1970s, when there were a bunch of evolutionary studies of them started, do one thing over time really well. The universe is expanding, yes, and in general, things are getting farther apart from each other as the universe expands. However, gravity is also at play as a major force in the universe. And so galaxies that are close to each other, especially in clusters and groups and rich clusters, often merge because of gravity. And so over time, primitive, tiny proto-galaxies that we see in the most distant Hubble images and things like that came together and merged to make larger galaxies in the modern universe. So a famous study that a pal of ours called Chris Consolis produced in 2016, you may have seen that, suggested that there may be 1 or perhaps as many as 2 trillion galaxies in the universe. Well, that's, if you go back in time and we're thinking of the early days of the universe, many of those galaxies combined to make larger normal galaxies later on in cosmic time. So one thing that we have to remember, of course, is that galaxies that are closer to us appear much more recently as they are closer to our time as we're sitting here talking today. And we're looking much farther back in time as we look farther away. Well, where do we start really with understanding galaxies? Well, at home, the Milky Way. This is a nice shot taken down at the ALMA radio telescope in Chile, showing the galactic center right overhead. And of course, as we see the light from the Milky Way on at least part of any night, any time of the year, you can see part of the Milky Way from a dark sky, of course. We're seeing the unresolved light from some billions of stars in our galaxy from within the plane of the galaxy. And it's fascinating because we can estimate that there may be about 400 billion stars in our Milky Way galaxy. We don't know exactly what the number of stars in the Milky Way is, because the faintest stars, the so-called red dwarfs or M dwarfs, are the most plentiful stars. Stars like our sun that are middleweight stars, and especially heavyweight stars that are very massive and live for a short time, are very small in number compared to M dwarfs that are reddish and very small, but are undergoing nuclear fusion, and they live on for a long, long, long time, and they're hard to see at long distances. So we have an approximation of there are about 400 billion stars in the Milky Way. Well, what do we think of the Milky Way? Well, it is was known to be a spiral galaxy, much like our neighbor, the Andromeda galaxy, that closest big galaxy to us, for decades, since Hubble's time. But we really know now that, and I'll talk a little bit more about this in a few slides from now, we now know since the last 20 years or so that the Milky Way is a barred spiral, that we do have a significant bar of material that cuts through the center of our galaxy, from which the spiral arms emanate. So we are a barred spiral, which was not known until fairly recent days, if you will. Our sun and solar system lie about 26,000 light years out away from the center of the galaxy in a small spiral arm called the Orion arm or the Orion spur. And it's a good thing that we're out in the cosmic suburbs, because as you get closer to the centers of galaxies, there are all kinds of dangerous things going on closer to the center. This is a Spitzer Space Telescope infrared view toward the center of our galaxy. And as you guys know, many of you know, if you go out and you look toward the summer Milky Way, and you look at a position, if you draw a line from the star cluster M7 up toward the Lagoon Nebula in Sagittarius, the direction of the center of our galaxy is about midway between those two objects on that line in Sagittarius. But we can't see to the center of our galaxy because there is so much obscuring dust in that direction toward the galactic center. So most of the stuff that we see in our telescopes in Sagittarius and Scorpius toward that direction is stuff that's about a quarter at most, about a quarter or even a fifth of the way toward the galactic center. But of course, an infrared image like this can penetrate more deeply toward the center of the galaxy. And it doesn't show us the galactic center, but it shows us a long way toward the center of the galaxy. We now know, because of the velocities of stars orbiting the center of the Milky Way, that we have a supermassive black hole in the center of our galaxy. It has the mass of about 4.3 million suns, 4.3 million times the mass of our sun. And it's a relatively small supermassive black hole, but you certainly wouldn't want to be close to it, of course, because we love science fiction, but unlike science fiction stories, if you got close to a black hole, or certainly the singularity in the center of a black hole, you would be pulled into a string of protons. And even if you could hypothetically travel through a black hole somewhere else in the universe, it wouldn't do you a whole lot of good if you're pulled into a string of protons that's 10 kilometers long. That kind of ruins your weekend. So there's science and there's science fiction, and we love to think about this stuff. But the centers of galaxies are dangerous places. There's antimatter, there's high energy radiation, frequently exploding stars compared to what we have in the boondocks here, if you will, and other hazards. So it's a good thing we are where we are as far as life goes. Well, this is the Andromeda Galaxy, a more modern shot than Hubble shot. This is a Tony Hallis shot of the Andromeda Galaxy. And like people, galaxies like to hang out in groups, some more than others. But galaxies hang out in groups mostly by gravitation. Our group of galaxies is called, Hubble derived this term in 1936 with his famous book, The Local Group of Galaxies. Not a very inventive name, but it's stuck and it's well known. And it contains at least 55 galaxies in our local group. The three large galaxies are the Andromeda Galaxy, which is the largest, the Milky Way, which is somewhat smaller, which is our own, of course, and the Triangulum or Pinwheel Galaxy M33 in Triangulum, which is another fairly good-sized spiral. Those are the three big galaxies in our group. Essentially, all the rest of the galaxies in our local group are little tiny dwarfs. You can see two of them that are the close satellites of Andromeda here. M32, the little fuzzball up above to the left of the galactic center here, and straight down below, and you can see some tidal warping of the envelope of it, which is really neat in this image, is NGC 205, which is another satellite of Andromeda. There could be as many as 100 galaxies in our local group, because just like stars with those little faint red dwarf stars, dwarf galaxies are by far the most numerous galaxies. And there may be some that are so obscured or partially being ripped apart that we can't see them as yet. Well, the Triangulum Galaxy M33 is an interesting one. It's a relatively faint object for observers because it has a low surface brightness. even though its total brightness is pretty high. It's about 3 million light years away, a little more distant than Andromeda. So of course, the light, we're seeing it as it was 3 million years ago, of course. The galaxy contains numerous pink areas of star formation, these so-called H2 regions, or emission nebulae, large emission nebulae. The one that's above and to the right of the nucleus of this galaxy here is so big and bright, it has its own NGC number. Some of you may have seen this in larger backyard telescopes. It's NGC 604, and it's one of the largest star-forming regions we know of anywhere. It's a very large star-forming region that is producing a little cluster of newborn stars. We know that although galaxies exist in groups, there's an enormous space between most of them and most of these groups. M33 is interesting, by the way, for another reason. We'll talk more about this in a moment, but black holes were a long time coming, the evidence for black holes. Black holes were hypothesized more than 200 years ago by an English natural philosopher, John Mitchell, who hypothesized that there could be regions of gravity that are so intense that they produce what he called dark stars. Well, we know of only a couple of dozen stellar black holes in the Milky Way because they're really hard to detect unless they're involved with an object that's luminous with them. But we know now, since the early 1990s and the Hubble Space Telescope, that most galaxies have a central supermassive black hole in them. The Andromeda Galaxy does, the Milky Way does, most galaxies that we know of that are large do. Dwarf galaxies, I mentioned, that are small, don't. But M33, while we're looking at it here, is an exception. It's a large spiral galaxy, but it does not have a central supermassive black hole, and why that is not yet known. So, although lots of space exists between most galaxies, and despite the universal expansion of the universe, funny things can happen in space. They're generally separated by vast distances, but local motions can send galaxies streaming in various directions. Gravity. Gravity is in force. It draws smaller objects in close proximity to larger ones. So the sky contains many examples, and this is a fantastic thing for us as astronomy enthusiasts. Many of these examples of interacting galaxies, like the antennae here, NGC 4038 and 4039, can be seen well in amateur telescopes. This is a really cool example. And you can see as these galaxies are merging and coming together, as they've spun in together, that these enormous long tidal tails of material are streaming off of the galaxies. So remember, we get to see sort of one cosmic frame at a time in a cosmic movie that's going on, but the time is so long compared to human lifetimes, and the distances are so large that we see essentially one cosmic frame in the movie at a time. Well, over time, galaxies often merge, and this is a well-known fact now of galaxy evolution. Over time, galaxies often merge, especially in groups, to form larger structures. The Milky Way may have begun as 75 or 100 small proto-galaxies long ago that we now have in a relatively normal disk. This is another merging galaxy. This is not a terrible thing, the merger of galaxies. It's just what galaxies do. And we think that in our own case, the Milky Way's disk formed about 9 billion years ago, roughly. But it came together for a long time before that from all these proto-galaxies that maybe are similar to these faint blue galaxies that we see in distant object frames like the Hubble Ultra Deep Fields, and like the first image that President Joe Biden released a few weeks ago from the Webb Space Telescope as well. And we now know that there's a lesson in our future of galaxy mergers, and that is thanks to the Harvard Astronomy Department and our friend Avi Loeb at Harvard and his collaborators, because a study about a decade ago or so by them showed that indeed the Andromeda Galaxy is not only moving toward us, its local motion is toward the Milky Way, but it will merge with the Milky Way eventually. This is on the order of about 5 billion years from now, and we will have a chaotic galaxy that Avi and his collaborators nicknamed Milkomeda for the Milky Way in Andromeda. So as we move farther out into the universe, we encounter larger structures of galaxies, of course. The Virgo cluster is the largest nearby big group of galaxies to us, and it lies, of course, toward the constellation Virgo and Coma Berenices as well in our sky. It contains about 1,300 galaxies in the Virgo cluster, and its gravitational center is about 54 million light years away. So the local distance scale is that the local group of galaxies has our own little group has a diameter of about 10 million light years. So the center of the Virgo cluster is about 5 times farther away than the diameter of our group. And that's the largest nearby group of galaxies to us. Fortunately, because we love astronomy, and believe it or not, there will come one day a time long from now when we can't see anything but our own galaxy because of the expansion of the universe. That's not the case now, thankfully, as amateur astronomers. But thankfully now, dozens of bright galaxies in the Virgo cluster can be seen in our springtime evening sky. So we have a really good situation for observing galaxies as amateurs, at least for the next few 100 billion years. Well, the Virgo cluster, as most large clusters of galaxies, it contains all types of galaxies, including one of the largest nearby galaxies, the giant elliptical galaxy M87. The galaxy measures 120,000 light years across. This is only a little larger than the Milky Way. Our disk of our galaxy is only about 100,000 light years across. This galaxy is about 120,000 light years across, not that much larger. However, this is a spherical galaxy. Galaxy disks are very flat, and this spherical galaxy, although it's not much larger in diameter, has about 200 times the mass of the Milky Way. It's a very large giant elliptical. And I don't know if you can see on your screens, very close into the center of the galaxy, there's a tiny, tiny little white line, a jet going up to just the above and right of the middle of the galaxy. I don't know how well our images are coming through, but that's actually an image of the jet of material that is being shot out of material that's not falling into the central supermassive black hole in M87. This, by the way, the central supermassive black hole in this galaxy is the one that was so-called photographed, the first image of really what is a shadow of the black hole a couple of years ago. You might remember that now. And this black hole weighs about 3.5 billion solar masses. So that's on the order of about 1,000 times more massive than the black hole in the center of the Milky Way. A very, very massive black hole in this galaxy, which is why this was the first one that the Black Hole Imaging Project tried to image and did image. And you might see, I don't know what our image quality is here, but there are many, many faint little stars in and around the halo of this galaxy, and these are not stars. These are globular star clusters. Our Milky Way has about 200 globular star clusters, old stars in spheres. You're familiar, no doubt, with the Hercules cluster, probably in Omega Centauri and some others. Well, our galaxy has about 200 globular clusters, these old stars that formed very early on and did not fall into what was assembled as the galaxy's disk. They're very old stars, older than the disks of most galaxies in most cases. Well, M87 doesn't have a paltry 200 globular clusters. Some of what you can see here are globulars around M87, and it has 12,000 globular clusters around this galaxy. So this is a huge galaxy that near the center of the Virgo cluster has consumed many of its galactic neighbors in the past to build up to this size. Farther away in the cosmos lie more exotic galaxies. Here, this is a famous distant galaxy called the Einstein Cross. And this shows that Einstein, again, was right over and over and over with his theories. The faint galaxy in the center, you can see there's a tiny little dot in the center of this galaxy, and then there are 4 brighter images, star-like images around it on each of the sides. And what's happening here, this is the light from a very distant, active young galaxy that is very energetic, that is directly behind this galaxy that we see with a faint disk. And so what's happening here is the galaxy of this, the gravitation of this disk galaxy that we see faintly in this image is bending the light from the distant galaxy that is exactly behind the nucleus of the closer galaxy and creating these 4 illusory images that is called an Einstein cross. So galaxies can act as cosmic lenses for us as well and show us artifacts of the extremely distant universe that we couldn't otherwise see. And again, don't bet against Albert Einstein. He's right every time. All right. Well, we're making our way farther and farther out. And as I mentioned, the deepest images of the universe made. Now, this is not true anymore. I haven't revised this talk in the last 6 weeks, but the James Webb first image that was released is deeper than this now, but we'll set that aside for the moment. This is one of the deepest images taken of the universe. This is the so-called Hubble Ultra Deep Field. And you can see there are a couple of stars in it that have diffraction spikes, but essentially everything in this field is a galaxy. There are 10,000 galaxies in this field, which represents, if you held a pin, the top of a pin at arm's length against the sky, that's how much sky we're looking at here, a tiny, tiny piece of sky. More than 10,000 objects, almost entirely galaxies, are in this. And you can see the faintest galaxies are very tiny bluish blobs in this image. They're the most distant galaxies up until the Webb image that have been imaged before. And these are the proto-galaxies that came together later in cosmic time to form normal galaxies that we know of today, including our own Milky Way. Well, just when we thought we began to understand galaxies and galaxy evolution, and it turns out that most galaxies form with angular momentum and a disk, a rotation, analogously to how solar systems and stars form, with matter coming in that creates some angular momentum that creates some motion and a disk. So how do you get elliptical galaxies? Well, you get these big balls of elliptical galaxies through collisions and less order. And that wasn't known until relatively recently either, exactly what was the path of galaxy evolution. So just when that started to be understood in the 1960s, more mysteries cropped up. thanks to Caltech and Martin Schmidt, an astronomer studying distant objects there. And he began to look at some of these objects that were not understood at all, that were bright radio sources, quasi-stellar objects that appeared to be star-like, but were emitting enormous amounts of energy in various parts of the spectrum. So there began to be an astrophysical zoo of strange objects that really confounded astronomers in the 1960s and 1970s. And it wasn't until the 1980s, and then eventually with the Hubble Space Telescope being repaired and online in the early 1990s, that we really began to understand what was going on here. A large number of high energy, very distant objects began to be cataloged. Quasi-stellar objects, like this is 3C273, and you can see near the bottom there's a jet of material that appears to be shot out of this distant star-like object. So-called BL Lacertae objects from a weird variable, irregular variable star in the constellation Lacerta. They've more recently sometimes been called blazars. Seyfert galaxies, high energy, unstable galaxies, first studied by the American astronomer Carl Seyfert, who was at Vanderbilt there in Tennessee. A whole panoply of weird high energy objects began to be discovered, and this really confounded galactic astronomers for a long time. Until the 1980s, when it dawned through a various studies on these astronomers that all these different strange objects, about 8 or 10 kinds of weird high energy objects, were really one object. And they were different because of the geometry by which we were observing them. So they all represented objects that turned out to be distant galaxies that had supermassive black holes where the material wasn't all falling into the black hole, but a lot of it was being emitted in various high energy realms. And we were seeing them as different kinds of critters, if you will, because of the orientations, the distances, and other variants. They were all artifacts of black holes spitting out energy in the early universe. Here's a fantastic example of one. This is Perseus A, which you may also know as NGC 1275, the most active and energetic galaxy in the so-called Perseus galaxy cluster. And you can almost just see, looking at this image, the chaos that's going on in this galaxy. You know, it looks like a distorted maelstrom with, you know, fingers of gas coming out of it and dust in front of the galaxy. Well, this is a really active and hungry black hole engine that is going on, swallowing lots of material, accelerating material that's being spit out and ejected because it's not falling within the black hole's event horizon. And there are lots of objects like this in the universe. What they don't devour comes out in jets and in high energy emission. And now we understand, as I mentioned earlier, that most normal galaxies, not dwarf galaxies, but most normal galaxies in the universe have a central black hole. It's not an unusual thing, it's an ordinary thing. And we didn't know that until the 1990s, when the Hubble Space Telescope was repaired, and a couple of groups of researchers, chiefly the one at Texas, where DeValcalers was, also now led, though, in the 1990s by John Cormandy and by Lewis Ho. And they started observing galaxy after galaxy after galaxy and seeing evidence of black holes in their centers. So as galaxies evolve, however, black holes become quiescent. They quiet down, generally speaking. Early in the universe, we saw quasars. We talked about BL Lacertae objects, Seyfert galaxies. Early in the universe, these black holes are really active and they're emitting a lot of stuff, and they're easy to see because there's a lot of material around them. And as galaxies evolve over time, they devour most of the material near them. And these galaxies, these black holes quiet down and they essentially go to sleep. And that's what's happened with the black holes in the centers of most normal galaxies like the Milky Way and the Andromeda galaxy. We have what are essentially dormant large black holes in the centers of our galaxies. Now, if a gas cloud or a cluster of stars should, by its motion, get kicked into the black hole, it would wake up and emit a lot of energy again. And so there can be episodes of black hole activity that's sort of like a cosmic flu. And when we do have that collision with the Andromeda galaxy in the future, that will undoubtedly happen. There will be enormous activity and lots of energy in the collision and merger of those galaxies, and we will have a big chaotic mess. And if we have any descendants around at that time, they will have a tremendous show to watch in our sky. Normally, galaxies exist in a gently balanced state between stately grace and internal upheaval. This is a little group of galaxies that are all close together, but fairly stable. Sometimes, though, throughout their lives, material will get close to these central engines, if you will, and we will have a crazy disruption event going on that also can create a lot of new star formation, by the way, as well. This may not be true, and we will never know in our lifetimes, but I like to think of the future collision of Andromeda and the Milky Way as something like our friend Centaurus A in the southern sky, a beautiful galaxy that's an elliptical galaxy that's fairly active. It's a merger of two normal galaxies that now is a big elliptical chaotic mess. And it has this incredibly prominent dust bar around the central portion of the galaxy. And you can see there's a lot of star formation going on in front of that band of dust. And this has all happened because of the merger of this galaxy, making the high energy parts of the galactic center energetic again. And so maybe, we'll never know, but maybe something on the order of 6 to 7 billion years from now, when our sun becomes a planetary nebula, by the way, and our solar system is kaput for planetary habitation, maybe the Milkomeda will look something like this. Well, to step back and make everything even more confusing for a moment here, we all probably have heard of cosmic inflation, the idea from the 1970s that Alan Guth and Andre Linde and others came up with. And there's a lot of evidence for this, that very early in the first second after the Big Bang, the universe almost instantly went from the size of about a pea to about the size of a grapefruit. And for reasons we can't go into today, because that's a whole nother lecture, cosmic inflation may well likely have happened because it would explain cosmologically a lot of what we see observationally later in the universe that we now have. So one of the slightly disconcerting things about cosmic inflation is that if inflation is true, which most cosmologists believe it is, then the visible universe that we see is not the whole universe. And in fact, the universe could be infinite, which sounds like a bad Star Trek episode, but it could actually be true. But let's set that aside. Let's set cosmic inflation aside. Even if the whole universe is the visible universe that we see, then the universe is what we call rather large. Very conservatively, I mentioned that we have about 400 billion stars roughly in the Milky Way. We know that there are about 100 billion galaxies in the universe. We know that a lot of those galaxies, however, are dwarfs. So let's make a conservative estimate and say that there are something like 10,000 billion stars in the universe. That's a lot of stars, even in the visible universe that we know of, setting inflation aside. We see planets pretty much everywhere we're looking relatively close by us in the Milky Way, with the exoplanet searches that are going, TESS right now and its predecessors, and other future telescopes will continue that search. Planets, as we would expect from understanding how solar systems form, are common. And we know through spectroscopy, through looking at getting back to my dad, the chemist here, we know that looking at the spectra of objects and understanding their chemical composition, that chemistry in the universe is uniform everywhere. We understand the elements and we understand chemistry and how they work, and we understand how organic chemistry works as well. And we know that the stuff that makes up the basic building blocks of life is out in the cosmos. The only sample of cometary material returned by the Stardust mission, by the way, to Earth in 2006, contained the simplest amino acid, glycine, in comets. And we know that lots of meteorites and other things have complex organics in them. So the stuff of life is out there. And we know that there are a tremendous and almost unimaginable number of galaxies and of potential worlds orbiting stars out in the universe. So one of the things that we all like to think about, of course, is how common is life in the universe? Well, Carl Sagan used to talk about this all the time. You know, we can think by odds that life must be unbelievably common in the universe, understanding chemistry and the numbers game. However, we only know of one place in the universe thus far, right here, where we know of life and that life exists. So this is one of the overarching future directions for research with galaxies and with stars and with planets and with everything is, you know, how common is life in the universe? This is driving a lot of our interest in understanding all of this stuff. We don't know. And of course, if you were gambling with Carl, Carl would say that life must be very common throughout the universe, even sophisticated life. Forget microbes, you know, being down, you know, in subsurface aquifers on Mars, which may one day be discovered. We don't know, who knows. But even civilizations could be very common because of the numbers game and because of what you need to have to get organic molecules replicating. However, the distance scale is so large in the cosmos that it's very, very unlikely. You know, again, I hate to beat up on science fiction. We love science fiction and imagining, you know, what's out there. But the cosmic distance scale is so large that traveling physically from star to star is almost unimaginable in the amount of energy it would require to move mass. Photons bouncing around on our computer screen and from lights and seeing the images of each other and so on can move at the speed of light because they're massless. But to move things that have mass requires a lot of energy. And remember that the distance scale is large. If we take the distance between Earth and the sun, 1 astronomical unit, as 1 centimeter, so that's a very small distance between my fingers here. We've physically traveled the longest travel we've done thus far as humans together to the moon. We hope we're going back to the moon, but we've gone to the moon. That's an almost infinitesimally tiny, invisible piece of that distance from Earth to the sun. The edge of the inner edge of the Oort cloud, that is the inner edge of the physical boundary just of our solar system on that scale. I told you I watched the Packer game last night, Imelda. On that scale, the inner edge of our solar system, would be 10 football fields off to the right there. And the distance to the nearest star, Proxima Centauri, 4 times greater distance than that. So even if life is abundant in the universe, as Carl Sagan used to like to say, it's very unlikely that we will have them land in Central Park and we'll go to dinner with the aliens at, Tavern on the Green. Communicating and having evidence of other civilizations through SETI is quite possible. Physically traveling around, how do you stock a spacecraft, at the highest velocity that we can realistically understand through physics for a 100,000-year journey to the nearest star? You got to put a lot of stuff in the pantry, to make that journey. It's really unrealistic, probably, to think about physically traveling to other stars. So Carl Sagan used to like to say that life could be abundant in the universe, but it's as if there is one person in Australia and another in the Central Plains of Oklahoma, and they may very well never meet. So that's kind of the bottom line of the realism of the cosmic distance scale that Hubble got us going on, much as we may not like it to accept some of these things. We can still have our, Star Trek and our stories. That's good stuff. So to end on one thing here, if I may, I hope I haven't gone too long. As Abraham Lincoln used to say, once I start a sermon, it gets to be too much work to stop. I haven't looked at the time, forgive me. But one thing that we're just on the cusp of understanding is that galaxies may have zones. And this is understanding this business of chemistry and life and galactic habitability and the numbers of galaxies. Galaxies may well have zones where life is more likely to last longer than other places within a galaxy. I mentioned that, we're about 26,000 light years out from the galactic center. For one thing, now we believe that rocky worlds offer the best hope for life, and these mean metal-rich stars. A galaxy like the Milky Way, because of that, may have a habitable zone, mainly in the spiral arms, and from about 10,000 to about 30,000 light years out from the galactic center. Farther out may mean fewer metals, and farther in may mean greater dangers. So we may be in a relatively quiet, boring place in the galaxy, but in the best place region that one can be to be a living being and be, well, I hate to say with the, politics of the last few years, to be in a relatively peaceful place. We could have a more peaceful civilization here, but as far as the galaxy is concerned, we're in a relatively peaceful place. So that's where we are about 100 years after Hubble's key discovery of taking that famous plate of the Andromeda Nebula and beginning to revolutionize our understanding of galaxies in the universe. And I hope that was enough interesting detail, and I hope I didn't go on too long. We didn't talk about all 100 billion galaxies, but I'd be happy to stop now and to take any questions that anyone has. Thank you very much.
Thank you. Thank you so much, Dave. Actually, there are a lot of questions. There are a lot of questions already. And what is nice about all of these presentations that we are having, including yours, is we learn a lot of things. And first time I've heard about the term Milkomeda.
Well,
and actually,
and I packed a lot of stuff into that. I hope it wasn't too much, but there's practically all of the stuff that I talked about, we've learned since Tim Ferriss's book. This is all mostly stuff that we've learned in the past 10 to 20 years, which is quite amazing. We are in a golden age for being interested in astronomy. We really are.
Yeah.
Jet,
And,
I have to say, I have to add, Dave, I can listen to you the whole day. Don't worry about that. This is such an inspiring and, it's really unbelievable. That the way you delivered it also is very good.
Well, thank you. You're too nice. And where do I send the check, Imelda?
Anyway, Dave, we have to go now into the Q&A because there are a lot
Yes.
of questions that
Yes,
came
yes.
in. And I'll read them as much as possible the way they were asked, but in the sequence they were asked. But here, one of the first questions is, when the James Webb Space Telescope creates its own ultra deep field, what do you think the image would reveal?
We have been lucky enough at the magazine to be pals with the project scientist, John Mather. And he's also involved with this Starmus Festival that I'm involved with. And he wrote a story a few months ago for Astronomy introducing the objectives of the telescope. And one of the primary reasons for the James Webb Telescope ties into galaxies. And that is that we know in the early universe that galaxies existed, that stars existed, and that black holes existed. And you know what we don't yet know? The formation sequence of matter in the early universe. Did galaxies come first and then black holes formed in their centers and stars turned on in their disks? Did stars form first and then gravitationally come together into galaxies? Did black hole seeds form first, around which galaxies formed? We don't know the formation sequence of the earliest matter in the universe, and that's specifically one of the reasons why the Webb telescope was built, to answer this question. So we should see, after some time and analysis and observations, how the earliest matter in the universe formed. And that's going to be very exciting and a big, big deal in astronomy and cosmology when we find that out.
Thank you, Dave. There's a cosmological question about following this question, but I think you touched on this a bit before in your presentation. Will the universe continue to expand forever, or will it collapse on itself?
Will it expand forever or collapse on itself? And that was one of the great questions that was an argument between various camps of people. It involves the Hubble constant, a fancy mathematical belief that was argued about for about 50 years. And we still don't know the answer to that, but the evidence from all sorts of ways of cosmology and satellites, the most recent one being the Planck satellite, how we get the most important cosmological parameters that we know, is that the universe does not have enough mass to halt the expansion and to contract. And, Fred Hoyle and others for years thought there was, a repeating, big bangs and a contraction and, a so-called steady state universe. That appears not to be the case. The evidence is pointing rather heavily toward the universe expanding apart forever and cooling, and trillions of years from now having a very dark, very cold universe where these tiny little red dwarf stars are all that's left that are burning, if you will, that are fusing. So a cold, dark, lonely ending. Again, forgive me, this is not, the most uplifting, result of all time, but it is science. So the answer is we don't know, but the evidence is strongly pointing toward a long, cold, dark end of a single universe that we have, and no contraction and repeated Big Bang.
Thank you, Dave. Going back to the James Webb Space Telescope, are there studies planned for studying galaxies with the James Webb Space Telescope, especially in the infrared?
Oh, yes. Yeah. The Webb Space Telescope is not, it goes into the mid-infrared, unlike Hubble. So there are numerous research projects and studies that are planned, and even some of them taking place already, that there'll be dribs and drabs of information about, and some more images released, of course, we hope soon. But many, many studies of galaxies planned, looking at them in the infrared, and therefore understanding, for one thing, star formation in galaxies much better than we do now. Yes.
Thank you. And again, another question about galaxies and black holes. Do all galaxies have black holes in the center, or is it only on more massive galaxies like the spirals and ellipticals?
The understanding that we have that began in the early 1990s with Cormandy and his group I mentioned is that most all normal galaxies have central supermassive black holes. There are a few exceptions. I mentioned M33, that's an exception that doesn't have one. That's a normal fair-sized galaxy. But dwarf galaxies, which are numerous, are not massive enough to have central black holes. A few of them do, but most don't. So the bottom line is that we believe the great majority of galaxies, except for dwarfs, do have central supermassive black holes. And they range, ours is pretty small, if you will, at a few million solar masses, but they range all the way up to some of the largest ones known include M87, which I mentioned, at several billion solar masses.
Well, related to this question about black holes is a question, one of the first questions in our chat box. Mostly I heard about black holes at the center of galaxies, and I understand that black holes are a result of supernovas. Would there be possibility of black holes lurking in the space between galaxies?
Yes, that's a really good question. There should be huge numbers of stellar black holes in our galaxy that are undetected yet, and maybe even enormous number, millions. And yes, there could be substantial black holes, and we wouldn't really have a good way to detect them, that are in the space between galaxies. Absolutely, yes.
Thank you. Next question, Dave, is in 1987, a supernova became visible in the Large Magellanic Cloud. What are the chances that we would see another supernova in the Milky Way in our lifetime?
They should be good. We are, you could say, statistically overdue for a supernova in the Milky Way, and even for a supernova in a very close galaxy like in the local group for us. So we're kind of overdue, just as we're overdue for a really great super bright comet that's right overhead, invisible for 6 months. We're overdue for one of those again too. But yeah. You can't predict them easily. We do know of highly evolved supergiant stars. Betelgeuse is one of them. When there was some dust that was in the atmosphere a year and a half ago or whatever it was of Betelgeuse, people were maybe it's getting ready to go supernova. That would be an incredible thing in our sky. It would be a daytime star at that distance in our sky. But the problem is that we know that Betelgeuse and stars like that are close to us in the galaxy will go supernova, but it may be on the order of something like 500,000 years. So don't hold your breath on Betelgeuse or other nearby stars. You can find some other hobbies in the meantime while we're waiting for that, nearby supernova. We are overdue for a bright Milky Way supernova. But unfortunately, we don't seem to be on the cusp of an obvious one near us that would be really exciting if we had one.
Thank you, Dave. Here's another question. It seems that the deeper we look and the further back in time we go, the weirder and more exotic galaxies look. Were galaxies more active and interacting more in the early age of the universe, and galaxies are now becoming more stable?
That's a really good question. And the short answer is yes. They were weird. They were not so normal. They have generally, as galaxies have merged and evolved, have settled down into more normal, quieter lives over time. So the short answer is yes. On both counts, that's absolutely true. And there are exceptions because especially in rich clusters, there are mergers and collisions and, tidal distortions and crazy things going on like that. But there were more small galaxies long ago, way back in time, doing strange things and with more collisions and more mergers and more weird tidal gravitational effects between them. So the short answer, that's a great question and one that you don't hear very much. Short answer is yes.
Thank you, Dave. Now, there are a lot of questions about black holes. So here's another one. Do
Everyone
astrophysicists
loves
know what
black
happens?
holes.
Yeah. Do astrophysicists know what happens to the matter that goes into black holes? Are we getting proof of white holes or wormholes?
That's a great question. And, unfortunately, he was on our board along with us. The great Stephen Hawking is no longer with us. He was on our STARMUS board, but a guy who's involved and will be there a couple of weeks from now. We're having another meeting in Armenia, a science festival, and the great Kip Thorne will be there. He's probably now he was Stephen's best friend. He's the remaining world's leading expert on black holes. Stephen, just like Avi Loeb, I would posit at Harvard, they love to put a few things out there and see what the reaction is going to be. So there's been a lot of writing, about wormholes and how you could travel in space and time through a black hole. And this is hypothetically, mathematically true to another place and time in the universe, if you will. This is the basis for 100 million sci-fi stories, of course. And there's some mathematical truth to that. However, there are black holes and there are black holes. So this is kind of a long answer, forgive me, but there are supermassive black holes and then there are stellar black holes. And the gravitational fields involved with the event horizons passing through into the black hole are different for those masses. Okay, if you approached a stellar black hole, you would be spaghettified, as I mentioned. You'd be pulled into a string of protons and that would ruin your whole weekend as you approached it even. And then you'd go into it and then there's a singularity inside and you'd be crushed into an infinitesimally tiny point of matter that, and you'd be in there forever. So that would not be such a great result. Now, the interesting thing is, and this is written about at length, was written about by Stephen, but Kip Thorne has a great classic book that's out there called Black Holes and Time Warps. And he writes all about this in this classic book from the 1970s. You could approach and even pass through the event horizon of a supermassive black hole, the ones in the centers of galaxies we've been talking about, and not even feel the gravitational effect of that. So you would survive passing into a supermassive black hole. You may not even know you had done it. However, the problem is, even if it's a wormhole, and see the, writings about that, there's still a singularity in the center of the black hole in which you would be crushed into an infinitesimally tiny point. So with black holes, there's the mathematical hypothesis of what could happen mathematically, and then there's the practical reality of what would really happen to you. And it would be a bad outcome with the singularity for you with any type of black hole. You'd be done, toast. So I wouldn't recommend trying to travel through a wormhole. It wouldn't work out well in practical terms.
Thank you, Dave.
And Kip loves to talk about this and joke about it. And he's going to be talking about it, by the way, again at STARMUS in about 3 weeks here in Armenia.
Thank you, Dave. I would just like to ask this question because I was always wondering about this now. Why do we find black holes inside the center of galaxies? So and related to this is, would black holes have been created in galaxies over time? Or did black holes form first and create enough gravity to pull in material to create galaxies? So sort of like a chicken and egg question.
Yeah, chicken and egg question of black holes in the centers of galaxies. And the short answer, it goes back to, some of the great astronomers like Jay Gallagher. I remember Jay Gallagher standing there lecturing about galaxies at the Texas Star Party a whole generation ago in the 1990s. And he said, if you think that if an astrophysicist tells you that we know the answers to all these questions, he's full of, and then I won't say what he said, even to a Texas Star Party audience. The short answer is we don't entirely know. And this harks back to Webb may answer that question of what was the genesis of black holes in the centers of galaxies. Presumably, it was because there's so much mass and therefore gravitational attraction concentrated in galactic centers, even early on in the lives of galaxies, that supernovae, massive dying stars that remember live short lifetimes compared to boring, ordinary low mass stars, were attracted to the mass in the center of the galaxy and exploded and in catastrophic supernovae that created black holes. And then you had a whole series of black hole mergers, making black holes more and more and more and more massive over time. That's presumably what happened, but we don't absolutely have the evidence for that yet, and maybe Webb will.
Thank you. So hope that the James Webb Telescope will answer that mystery.
Yes,
Uh,
absolutely.
yeah. Let me go now to a more personal question here. Can you tell us about your meteorite and mineral collection?
Oh,
From a meteorite from one of our amateur astronomers who loves meteorites. Yeah.
sure. Yeah, I should have, I should have brought a few examples down to show, or maybe I can come back much later when you've run out of other more interesting things and show some examples of that. But one of the things that I had having a professor father was contaminating me with all sorts of strange interests, So, and this is, when you're a teenager, you get interested in other things, i.e. girls, but if you're infected with these interests when you're a kid, they come back in a big way to you later. And so my father was interested in mineralogy along with his chemistry, and traveling in the early days, even back to the 1920s and 30s, to various mines in the United States when you could actually access them and so on, and put a rock and mineral collection together. So he passed that down to me, and that got me infected with interest in what, after all, is planetary geology, minerals, how the universe makes planets, is mineralogy. And so it's really an allied interest of astronomy. So once you go to the Tucson Gem Show, which is how you collect minerals now, because the mines are all closed off because they don't want people falling down a mine shaft and suing them for $1 billion, So now you collect stuff at a show, and that really got me interested in mineral species and all that kind of thing. And that, of course, isn't far away from meteorites, because to hold pieces of asteroids for the most part in your hand is really cool as an astronomy enthusiast. And of course, the most exotic meteorites as well are lunar or Martian meteorites as well. And I'll tell you one quick story. There's a guy, Bob Haig, who lives in Tucson, who's a great meteorite dealer and a legend in that field. And my pal Michael Bakich and I went over to his house one day years ago, and here's how the meteorite world is. He said, we opened the door and he says, "Hey, Dave, here, catch." And I did. And it was a rock that was, palm sized. And what are you doing, man? And it was the main mass of Zagami, which is the largest Martian meteorite on Earth, which he had just tossed me. This is a rock that's worth, a couple $1 million, and he's the owner of it. And I, don't do that, Bob, But once you get hooked on that stuff and interested in it, it's like books and, historical stuff, there's no getting out of that. So be careful with rocks and minerals and meteorites, because those collections, like books, tend to multiply over time while you're not looking. But I do have a modest collection of a couple hundred meteorites that mostly have been given to me. I haven't been really going after a lot of that stuff, but I have a couple thousand nice mineral specimens that I've been very passionate about as well. Gives you something to do during the daytime. Huh?
Thank you, Dave. Hope we can see them in the future some other time.
Sure. Anytime. Yep.
I would. There's another interesting black hole question here in the chat
Yep.
box. Question from Mr. Ike Jason Rollion. Hello, sir. How do supermassive black holes differ from stellar black holes in terms of their singularities? Thank you so much.
That's another really good question. And the short answer is we don't know entirely. We believe that the singularity itself would act essentially in the same way on normal matter, but we don't know except mathematically. So that's, and will we ever know? That it reminds me of a question like, do we live in a multiverse? Are there other universes? Mathematically, there very logically could be other universes, and we could have this network of universes in which we're in a bubble and there are spaces between the bubbles, and mathematically it makes sense. But observationally, we are stuck in our universe, and by definition, there may never be evidence observationally of other universes. We may never have evidence of the differences of how singularities might work in black holes depending on their different masses. That's a really good question. And we don't know the final answer to it. This is good because astronomers and astrophysicists and cosmologists and planetary scientists, they're not going to be out of work anytime soon. Because we make all these discoveries, but then that leads to another 10 questions for every discovery.
Thank you, Dave. Maybe now, we can ask our panelists if they have questions for Dave.
Well, Dave, it's not a question. But by the way, first of all, we'd like to thank you for being generous with your time. And it was really, really enlightening. And I hope all the listeners were able to take away something from your lecture in understanding about galaxies. So mine is not a question, but more like an invitation. Perhaps in a future webinar, we can invite you again to talk about meteorites.
I'd be happy to. That would be great fun. And I could show some pictures of meteorites on the screen and so on and talk about them. It's really, there's something that, and you can get, I'm not, I don't have a meteorite company, don't worry. But, there are meteorites that you can get very simply, iron Campo del Cielos, for $5, that kids can go to a show and get, and holding that in your hand, that's the metallic part of the core of an asteroid, is really electrifying. And then there are specimens all the way up to hand-sized lunar specimens that I've seen marked for sale at $400,000. So the spectrum of collecting this stuff, of getting into it, runs the whole gamut. It can be a very simple and easy thing to get into in an easy way, but there is a risk. It can be addicting.
Yeah. I'm sure a lot of people are interested in starting their own collection, and this would be a good way of introducing them to the hobby, and also telling people how to distinguish between meteorites and meteorons.
Yes, and absolutely.
Without breaking the bank.
Yes. And I'd be happy to do it. Yeah. Imelda and Ed, let me know, at some future point when you'd like me to.
We're going to schedule that, Dave.
And earlier, before your talk, Imelda showed you a picture that was taken during our wedding anniversary.
Why don't we get it?
We didn't tell you. On our 25th wedding anniversary, we bought a pair of wedding bands.
We actually changed it.
Yeah, made of Gibeon.
Oh, yes.
Yeah, we bought it from Bob Summerfield, Astronomy to Go.
Oh, he's a great guy.
Yeah,
and Gibeon is very nice because it's so hard. It can be cut so well among iron meteorites. And it also has a pretty high ratio of nickel. So, iron, not to get into all meteorite thing, but some iron meteorites eventually will rust and you have to take care of them. Gibeon is pretty rust resistant too, so it's perfect for things like jewelry. Yeah.
Yeah. I'm gonna have Edwin get it while I say something.
Excellent.
When you said that you answer one question and you have 10 more new questions.
Yeah.
And I think I have to say, Dave, that with what you're doing through the magazine, through your speaking engagements, through this webinar, we hope that we can inspire the future generation out there to continue, trying to find more answers, because our lifetime is not enough. One human lifetime is not enough.
Absolutely.
And I always say, our knowledge of this universe is based on what our instruments can detect and what our minds can comprehend.
Yes.
And we progress forward with new equipment and new knowledge. We begin to understand the universe more and more, but as you said, more questions. So it's a continuation, a continuing process. And it is up to us to inspire the future generation to go find the answer to the questions.
You couldn't be more right, and that couldn't be a more important point, Imelda. And yes, we're living in a golden age. Yes, we're finding the rate of discovery is higher than it's ever been. And yes, things like Webb should tell us how matter formed in the early universe. But a lot of the exciting things, we should have it for, let's hope 30 years to come. A lot of the exciting things that we'll find out are things that we can't anticipate now. That's very exciting too. We're in for a golden age of perhaps surprises too. Let's hope.
Yeah.
So just to show very quickly.
Yeah, those are great. Yeah. Perfect.
Yeah, that's a Gibeon.
Excellent. Yeah.
Okay. Sorry for taking up too much time. Okay, turn.
Dave, I have
Yeah.
another question.
Yes.
Speaking of the golden age of astronomy, especially I think now in amateur astronomy, we're in a golden age as well in terms of availability of equipment and for imaging, for example. And I noticed we are having we have a lot of in the audience who are astro imagers. No? So can you give them some advice regarding imaging galaxies, especially the amateurs? Is it possible for them to contribute also to science and not just taking pretty pictures of galaxies?
It is. I mean, it's easier to do imaging now, believe it, with all the complexities and the fact that the dark room is now on your computer and there's so much to think about image processing and so on. It is easier now than ever before. Couple of things. I mean, for a long time, this was 30 years ago, professional astronomers used to say, yeah, you can make a real contribution from amateurs, wink. And you didn't, they were very supportive and encouraging of amateurs, but you didn't really see a lot of stuff turning up in papers and so on. Now, the equipment and expertise that exists from amateurs, there really truly is a contribution that one can make to real science as an amateur astronomer, if one wants to. And there's nothing wrong with just observing things and taking pretty pictures too. And it's easier than it ever has been. When I bailed out of imaging myself very early on because I started Deep Sky Monthly when I was a teenager, and I had one season of doing some astro imaging with my 1976 C8, which I got. And in those days, there was no, the alignment, everything was sort of a big effort, and you had an illuminated reticle eyepiece and a drive corrector, it was called in those days, and you would punch buttons, and it was like being in a prison camp for an hour, one exposure, because you had to keep a star right on the crosshairs exactly for an hour. Well, now you have auto guiders and great auto alignment. So it's a lot easier than it used to be to do really good imaging. and we're stunned. We get stunned at the magazine because we get these phenomenal images of galaxies and so on sent to us from people we've never even heard of, and they've gotten the system, and they've been doing imaging, astro imaging, for 4 months, and they're phenomenal, the results. So if you want to get into it, now is the time. It's a lot better climate than it used to be. And yes, as you mentioned, you really genuinely can now, if you'd like to, contribute to real science.
Thank you.
I have a question. Well, yeah, hi,
Okay.
David. Yeah,
Peter,
first,
Hello.
yeah, congratulations again for the talk. Yes,
Thank you.
so it's not actually a question, but I would like to hear your opinion, because actually this thing that I would like to share with you is something like I've been asking myself for like a few years already, and I think this is the best chance that I'd be able to share it with you. So, is it possible that the reason for galaxies are moving away from each other is that they are arranged in such a way that they are all revolving around on an even bigger or greater object in varying orbits, much like a system, such as an atom where the nucleus lies in the middle and you have the protons and electrons revolving around it. And in an even bigger scale, you have the moon revolving around its parent planet, planets revolving around its parent stars, and stars moving around the galaxy center. All appears to have uh, like the same pattern from the smallest to the biggest. And this gives me the thought that there could be something in the middle of the universe where all the galaxies could be moving around it in various orbits, which could explain why they appear to move away from each other, because some galaxies could have smaller orbits than other galaxies. But they would tend to move faster and leave galaxies that have bigger orbits and so forth. Considering the pattern that you see, that serves as a clue that there could be, well, something functioning in the part of the universe. Yeah, so I'd like to
That's a
hear.
that's a really interesting set of thoughts and of notions that you bring up, and we don't really know a lot about any significance or not. There's a lot of random motion in the universe, and this reminds me of something that we used to ask Halton Arp and other galactic astronomers years ago, and that is there's something in chemistry called chirality, the handedness of molecules, and whether something is right or left-handed in how you see it, or it's an arrangement. And, this kind of is something you wonder about galaxies. Well, are there more, from our point of view, are there more spiral galaxies that are right-handed or left-handed? And if there's a difference, why is there a difference? And again, the short answer is nobody knows yet. So we need to stay tuned. But also the universe is expanding because of the origin point and the so-called Big Bang, which really wasn't an explosion. But remember, it's not just stuff within the universe that's expanding away from other stuff, but it's space itself is expanding over time. And so that's why, if you think about the speed of light and the origin of the universe 13.8 billion years ago, then one might just have a notion and think, well, how can the diameter of the universe be 93 billion light years then? And we don't have time to get into everything here, but you know what I mean? That seems awfully big for something that's the speed of light is the fastest speed there is, and the origin of it was only less than 14 billion years ago. Well, and the answer is that space itself is expanding. It's not just a box with things in it that are moving away from each other. So that interstitial 1 centimeter early in the universe becomes 2 centimeters and becomes 4 centimeters over time. Space itself is expanding. And again, we don't have time. This is the most popular question we get, which is also related to your really intriguing idea that you brought up. the most popular question we get all the time for our Ask Astro section in astronomy is, where is the center of the universe? And the answer is there is none. The universe has no middle or center. And this goes back to relativity and Einstein, and it has no edge either. And we don't have, this is another whole lecture to get into why this is. We don't have time for that. But there are only, you know, non-significant reference points that can be viewed, but there is no middles per se, you know, as a objective center of everything. You know what I mean? And we can talk about that at another time. There's a huge amount of stuff to talk about that. But the short answer is that the motions, as far as we know, are random, of things like galaxies and how they're moving, and how the direction of angular momentum to create a moving disk, either in a proto-solar system or a galaxy, appears to be based on random motions. But again, we don't know. So these are questions that maybe things like the Webb Space Telescope can begin to shed a little more light on. But it's fantastic that you're thinking about things like that, because those are the kinds of questions that could be on the next frontier of astronomy to figure out.
Thank you, Dave.
Thank you.
But I think we have to end this Q&A portion. Otherwise, we will spend the entire night here.
Sure. Yeah. Well, thank you so much for having me. It's really a pleasure to be with you and see so many old friends. Bless you all. And I know you're doing wonderful things with the organization and all the projects you guys have as well, and look forward to seeing you again.
And Dave, we would like to give you this small certificate of appreciation, and let me read it. This certificate is presented to David Eicher for his invaluable insights, experiences, and expertise shared with the participants of the webinar entitled Galaxies Inside the Universe's Star Cities, held as part of the ALP Astronomy Expert Series 2022, given this 20th of August of 2022, signed by President James Kevin T. and Vice President Jose Francisco Aguilar. Thank you so much, Dave. And we would like to have a sort of a picture, group chat with you before we.
Casey, will you do it?
Thank you very much.
Let's have we have a customary group chat with our honored guest.
Casey, can you do it?
Hello, do you hear me now?
Oh, can you do it?
Yeah, there. Yeah, I'll do it. Okay. 3, 2, 1, say cheese.
Cheese.
Okay, hold on. let me check if it went in. Okay, I'll take another one. 3, 2, 1. All right, I got it. Thank you for the talk, David. It was really wonderful, interesting.
Well, thank you very much. You know, you're obligated to say cheese in Wisconsin too, by the way.
Yes, that's true.
Thank you so much, Dave.
We should have
Dave,
said
thank you very
Wisconsin
much
cheese.
for attending our webinar.
Thank you, Dave.
Thank you so much.
Finally,
And
we finally met you, and not just your picture in the magazine.
Yeah.
Thank you so much.
Thank you so much, and bless
thank you so much. Thank
Good
you
luck
so much,
with
Dave.
everything you're doing, and I look forward to seeing you all again.
Go
Next time
back.
we'll hear you
Dave.
from meteorites.
Thank you, Dave. Yes.
And I think you're seeing Chris.
Thank you.
You're seeing Christopher. Go. It's
Bye-bye.
Carlos next.
Dave,
Okay,
I will
I think
call you.
Dave left already.
Oh, he's gone already.
Yeah.
Anyway,
Okay,
let me
so,
before we conclude this today's webinar,
Mhm.
I would like to thank all our attendees for joining us. We will be sending your certificate of attendance for today's webinar by email to all registrants who were able to join us today. As mentioned earlier, this is the 7th webinar in our ALP Astronomy Expert Series of 2022. We started this webinar series last April 23 with Dr. Jay Pasakoff. Our other esteemed speakers since then were Mr. Zolt Levey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, and today, Mr. Dave Eicher. We are so grateful to all our webinar speakers who very generously gave their precious time to share their knowledge and expertise to the world amateur astronomical community. We can never thank you enough. And if you want to review the talks, actually we have posted them, and we are posting this talk as well in our YouTube channel of the Astronomical League of the Philippines, as shown here. So kindly subscribe to our YouTube channel, and you can watch all the webinars that have been presented. And lastly, we would like to announce our next webinar, which is scheduled on September 24, Saturday at 8:30 p.m. Philippine Standard Time, or 8:30 a.m. Eastern Daylight Time. We will have a very timely topic in today's times of climate change. The topic is Turning the Telescope Back to Earth, the Challenges of Living in a Warming Planet, to be given by Professor Matthew Barlow, Professor of Climate Science of the University of Massachusetts, Lowell. And we will be posting the registration link for this free webinar at the webpage of the Astronomical League of the Philippines, and also on our social media and Facebook pages. Thank you so much again. Take care and clear skies always. For the panelists, I will be posting our Zoom webinar link shortly after this. So log in about 5 minutes.
Thank you very much. Thank
Thank
you,
you.
everyone.
Thank you very much. Bye-bye.
Bye, everyone.
Take care.
Thank you,
Bye-bye.
everyone.
Bye.
Thank you for attending.